Hi students, my name is Ms.L.DHARANI. I am working as Assistant Professor in Computer Science Engineering Department in S.A.E. Engineering College. Today we have discussed about the topic of instruction pipelining and hazards in computer architecture subject. So let us see what is pipelining. The pipelining is widely used in modern processor, and then pipelining improves system performance in terms of throughput. Pipelined organization requires sophisticated compilation techniques. So pipelining means more than one instruction's execution at same time. So that's why pipelining is widely used in modern process. So in modern process, most probably they are using more than one processor are executing at same time. Making the execution of programs faster. So why we have to choose for pipelining? So pipelining it's used, already we have discussed, more than one programs are executed at the same time. So use fast circuit technology to build the processor and main memory. Arrange the hardware so that more than one operations can be performed at the same time. In the latter way, the number of operations performed per second is increased even though the elapsed time needed to perform any one operation is not changed. Elapsed time is nothing but it's an starting and then ending time. In between the mediation time is called as elapsed time. Traditional pipeline concept. Pipelining does not help latency of single task. It helps throughput of entire workload. The pipeline rate limited by slowest pipeline stage, multiple tasks operating simultaneously using different resources. Potential speedup is based on the number of pipe stages. Unbalanced length of pipe stages reduces speed up time to fill pipeline and time to drain. It reduces speed up stall for dependencies. So dependencies means the second instructions almost depend on the previous of the first one result. So that's why it's called as dependencies. Difference between pipelining and non-pipelining. For this example, the first thing is normally three instructions are taking individual execution: fetch, decode, execute, write result for the first instruction. The second instruction also using compilation of the end of the fetch, decode, execute, write. So almost the three instructions are taking 12 minutes for compilation. At the same, the three instructions are executing in pipeline stage: fetch, decode, execute, write result. At the meantime, during the first instructions in the decode part, the second instructions are entering into the fetch unit. So this is meanwhile it's taking 6 minutes for compilation. So this is a major advantage for pipelining process. So it will be speed up the processor. Speed up is increase means automatically the performance of the processing will be improved. So this is for hardware organization for 4-stage instruction pipeline. So fetch instruction, decode, execute, store results. These are the 4 stages of pipelining. The in between B1, B2, B3, these are all the intermediate storage buffer. Okay, so this is a buffer. For example, the first instructions are fetched and then they put it in the buffer storage. Then it will be ready for executing the second instruction. So meanwhile, the buffer instruction, it's sent to buffer storage, they are sending the result to the decode part. Decode part is sent to the buffer. Again the decode register is ready for fetch the second instruction. So meanwhile everything it will be compiled at the same time. Idea of pipelining in a computer: fetch instruction, dispatch, decode instruction, execute instruction, write results. So the control unit first fetch the instructions, the buffer register. After that it will be sent to the fetch unit. The fetch unit fetch the first instruction and then send it to the buffer register. Now the fetch instruction is free. The area of the fetch instruction stage is free. Then it will be ready for fetch the second instruction. At the meanwhile, the instruction decode for the first instruction. Decode means they segregate the instruction. The third unit instruction execute for the first instruction for execution process. Meanwhile, the second decode stage is ready for decoding the second instruction. So this is a continuous process. So that's why multiple instructions are executing same time. This is the single cycle data path diagram. Okay, so the PC program counter, the program counter is always point out to the program counter is always point out to the address of the next instructions. So with the help of program counter, we have to get the one by one instructions, and the instructions are executed in this part. After finally we have to get the result in that multiplexer B. So this is for the 4-stage pipelining concept. So T1, T2, T3, T4, T5, T6, these are all the clock cycles, and then instruction 1, 2, 3, 4, 5. So we have to execute 5 instructions at the same time. So the first instructions are fetch, decode, execute, write. The second instruction meantime fetch, decode, execute, write. So these are all the processing steps in pipelining. So here also no instructions. Here number of stages are engaged. Instruction fetch. Instruction fetch means it's a stage, it's responsible for obtaining the request instruction from memory. The instruction and the program counter are stored in the IF pipeline register as a temporary storage, so that may be used in the next stage at the start of the next clock cycle. Instruction decode. The instruction decode stage is responsible for decoding the instruction and sending out the various control lines to the other parts of the processor. Decode means just for segregate the instruction. Segregate means what are the operands needed for this instruction, what are the opcodes. So it will be segregate the opcode and then operands. The instruction is sent to the control unit where it is decoded and the registers are fetched from the register file. Execution unit. So once the instruction is fetched from the memory, then we have to decode. Decode means segregate the operands and then opcode. Third one is execution. The execution stage is where any calculations are performed. The main component in this stage is ALU. The ALU is made up of arithmetic, logic, and then capabilities of doing the process. Memory and I/O. The memory and I/O stage is the 4th stage of the pipelining process. So the memory and I/O stage is responsible for storing and loading values from memory. It also responsible for input or output from the processor. If the current instruction is not of memory or I/O type, then the result from the ALU is passed through to the write back stage. Executing, decoding and fetching process in this diagramation. The first instruction, the second decode part, the third is the execution part. So the first instruction in the execution part means, meanwhile the second instruction in the decode stage, the same time the third instruction in the fetch stage. So this is the pipelining processor. So at a time more than one instructions are executing simultaneously. That means first instruction in a execution part, second instruction in a decode part, third instruction in a fetch part. So this is in a continuous process for completing the execution. Advantages and disadvantages of pipelining. So the most advantages is more efficient use of processor and then quicker time of execution of large number of instructions. The major disadvantages is pipelining involves adding hardware to the chip, like inability to continuously run the pipeline at full speed because of pipeline hazards which disturb the smooth execution of the pipeline. So the major disadvantages of this pipeline is hazard. So let's see about the hazards. Pipeline hazards. So hazards means it's nothing. For during the execution of the pipelining process, for the first instructions are fetch, decode, execute. Meanwhile, the second instructions are executing. So the second instruction, it will be wait for some more cycles. Clock cycle means that during the clock cycles, the process is not done. So the particular space is in an idle stage. So that idle stage is called in pipeline hazards. Pipeline hazards are conditions that can occur occur in a pipeline machine that impede the execution of a subsequent instruction in a particular cycle for a variety of reasons. That is, if a few instructions are at some stage of execution in a pipeline design, there is a chance that these sets of instructions will become dependent on one another, reducing the pipeline space. So that means the second instruction is always depending on the previous one, means so the second instructions are waiting for till the completion of the previous one. So that time the clock cycles will be idle. So that idle clock cycle is called as stage. So that's stall. So that stall is called as hazards in pipeline. So types of hazards. There are three different types of hazards in computer architecture: structural hazards, data hazards, and then control hazards. So dependencies can be addressed in a variety of ways. The easiest is to introduce a bubble into the pipeline, which stall it and limits throughput. The bubble forces the next instruction to wait until the previous one is completed. The first one is structural hazards. Structural hazards means where it will be occurs means most probably it will be happen in the resource conflicts. So that is called as structural hazards. So hardware resource conflicts among the instructions in the pipeline cause structural hazards. Memory, a GPU register or an ALU might be all used as a resources here. When more than one instructions in the pipe requires access to the very same resources in the same clock cycle, a resource conflicts as said to be arise. So this is called as structural hazard. For example, in this diagram, see we have to using for 5 instructions. In this 5 instruction, during the first instructions in the 4th clock cycle times read write result, at the same time, same clock cycle time, the instruction 4 also need for the memory for fetching process. So at the same time they are using that memory. So this time it's a conflict has to be occur, because the first instruction simultaneously the 4th instructions they are need for the memory help. So that time there is a structural hazards has to be happen. So this is called as structural hazard. So the yellow is specified for the memory access required, the blue is specified the memory access may be required. So for example, the first instruction the memory access may be required, at the same time instruction 4 also they are need for the memory for fetching process. So this is called as structural hazards. So how to overcome, the problem has to be solved means we have to segregate that instructions for the different clock cycles mode. For up to first instruction, second instruction, third instructions are using in one up to 6th clock cycle. Again the 7th clock cycles onward, the next 4th instruction has to be fetch, decode, execute, write, result. The next one is data hazards. So structural hazards means we have to discuss the resource conflicts. Data hazards means their full and full depends on the data. See, for the example, when the execution of an instruction is dependent on the results of a prior instruction that's still being processed in a pipeline, data hazards occur. See, in this example, the second instruction is waiting for till the completion of the previous one. For example, the first instruction add x3 x6 comma x5. So the content of x5 register and then x6 register, after that the resultant has to be stored in x3 register. So the second instruction subtraction is waiting for the result of the previous one, because the x3 is the one of the operand of the second instruction. So that time the clock cycle has to be idle and that some of the times. So that idle clock cycle it's called data hazard. Say example, for read write result in the clock time 5, T1, T2, T3, T4, T5 is in a time clock cycles. So up to the 5th clock cycles read write of the first x3. So the x3 is depending on second instruction as well as the third instruction as well as 4th and 5th. So for all remaining, all the 4 instructions are depend on the first previous one of the first instruction. So this time the clock cycles are idle waiting for the previous first instructions are completed. So this idle clock cycle is called data hazards. So the data hazards are classified by 3 types. Classification of hazard, flow through data dependency, read after write. This is when one instruction makes use of data from a previous instructions. So this is for read after write. So once read the content, after that it will be using for subtraction of the data. The second one is anti-data dependencies. So in this example, when the second instruction is written to a register before the first instruction is read, this is known as a race condition. In case of a simple structure of a pipeline, this is uncommon. WAR on the other hand can occur in some machines having complex and specific instructions. Output data dependency. This is the situation where two simultaneous instructions must write the same register in the same sequence they were issued. So this is write after write. So that means a same registers they are using for both the instruction. For example, add x0, x1, x2 means the first instruction is also using the same x0. The second instruction also using the same x0 for the resultant register. Control hazards. So control hazard is most probably happen in that we have to use it for some branching instructions or jumping instruction. That time the control hazards has to be happen. So branch hazards are caused by branch instructions are known as control hazards. The flow of program instruction execution is controlled by branch instructions in higher level languages. Conditional statements are used for repetitive loops or condition testing. As a result, when the decision to execute one instruction is reliant on the result of another instruction, such as a conditional branch which examines the condition's consequent value, a conditional hazard develops. For example, see in this instruction, three instructions are there, I1, I2, I3. So add, jump and automatically the second instruction PC is 404. Program counter is point out to the 404. So it's read the jump. So jump means automatically the controller goes to the jump instruction. The instruction is specified at the 640. The same time, the second instructions, that means the 408, the third instructions are waiting for till the completion of the previous one. So that time the control hazard has to be happen. So summary means the pipelining, overall view of the pipelining and then hazards. Pipelining attempts to maximize instruction throughput by overlapping the execution of multiple instructions. Pipelining offers amazing speed up. In the best case, one instruction finishes on every cycle and the speed up is equal to the pipeline depth. The pipeline data path is much like the single cycle one but with the added pipeline registers. Each stage needs its own functional units. Next time we will see the data path and control and walk through an example execution. The problem solving method for the based on the pipelining hazards, how they are asking for the questions. The first thing is consider a pipelining having 4 phases with duration 60, 50, 90 and 80 nanoseconds. Given latch delay is 10 nanoseconds for these 4 stages. So calculate the pipeline cycle time, non-pipeline execution time, speed up ratio, pipeline time for 1000 tasks, sequential time for 1000 tasks. The first solutions given 4-stage pipeline is used. Delay of stages 60, 50, 90 and 80 nanoseconds. Latch delay or delay due to each register is 10 nanoseconds. So these are the details they are given in that problem. So the first one, pipeline cycle time. So cycle time, maximum delay due to any stage plus delay due to this register. So maximum, first we have to find out the maximum due stage. So maximum due stage means, see 60, 50, 90, 80. In these 4 stages, which one is the maximum value? So we have to consider 90 is the maximum. So that's why we have to choose 90 ns plus 10 ns is the latch delay due to each register. So 90 plus ns, 100 ns for the pipeline cycle time. Speed up ratio. Speed up ratio, the formula is non-pipeline execution time divided by pipeline execution time. So non-pipeline is nothing to 80 ns. Non-pipeline means we have to add all the 4 stages nanoseconds. So 10, for example, 4 stages means 10, 60, 50, 90, 280. So it's in a 280. So non-pipeline stages is 280 ns divided by pipeline execution time, cycle time is 100 ns. So finally we have to get the speed up ratio is 2.8 ns. Part 4, pipeline time for 1000 tasks. Pipeline time for 1000 tasks, time taken for first task plus time taken for remaining 999 task. So the first task into 4 clock cycles plus 999 into 1 clock cycle. So 4 into cycle time 100 ns plus 99 into cycle time also same 100 ns. So 400 ns plus 999 ns. So totally 1,00300 nanoseconds for the completion of all the 1000 tasks. Sequential time for 1000 tasks, non-pipeline time for 1000 tasks, 1000 into time taken for one task is, so this is for sequential time means non-pipeline. So 280, already we have to calculate non-pipeline time is 280 ns. So 1000 into 280 ns is the resultant value of the sequential time for 1000 tasks. So the second problem, we have to two designs D1 and D2 for a synchronous pipeline process. D1 is a 5-stage pipeline with execution time of 3ns, 2ns, 4ns, 2ns and 3ns. While the design D2 has 8 pipeline stages, each with 2ns execution time. How much time can be saved using design D2 over design D1 for executing 100 instructions? So these are the 4 options. So let's see how to solve this problem. So cycle time in design 1, so maximum delay due to any stage plus delay due to means, so we have to find out 3, 2, 4, 2, 3. Which one is the maximum value means 4ns is the maximum. So delay is nothing delay, so that will be taken as 0. So 4ns is the cycle time. Execution time for 100 instructions in design 1, execution time for 100 instruction, time taken for first instruction plus time taken for remaining 99. So 1 into 5 clock cycles plus 99 into 1 clock cycle. So 1 clock cycle time is nothing, 4ns. So 5 into 4 plus 99 into 4, 5 into 4 20 ns plus 99 4 396 ns. So finally 416 ns nanoseconds. Cycle time in design 2, delay due to stage plus delay due to its register 2ns plus 0. So finally 2ns. So delay due to stage already they are given in that problem. Execution time for 100 instruction in design 2 D2, execution time for 100 instructions, time taken for first the same method, time taken for the remaining 99. So 1 into 8 clock cycles, because the D2 design has to be designed for 8 phases. So that's why 1 into 8 clock cycles, 99 into 1 clock cycle. So 8 cycle time 2ns, 99 into 2ns. So finally 214 nanoseconds. So find the time saved. Execution time in design D1 minus execution time in design D2. 416 minus 214. So finally 202 nanoseconds is the answer. So that's why the option B is the correct answer. Thank you. We will continue on next session.